Hi everyone. Today I'm going to talk about our work, Neural Language Modeling for Contextualized Temporal Graph Generation. This is a joint work by me, Aman, and Professor Yiming Yang. We are both from LTI at Carnegie Mellon University. So this is the outline of this talk. I'm going to introduce temporal graph generation. Then I'll talk about our methodology. I'll discuss some experiments and then we'll conclude. So the problem of temporal graph generation is as follows. We are given a document D and we want to generate a graph G where the nodes V are the events and the edges E are the temporal relations between those events. This task was first introduced in Temporal 3. There are many applications of this task, including in IE for clinical records, question answering, and so on. So just as a concrete example, on the left we have a document D, and on the right we have the corresponding temporal graph, and as I discussed, the nodes are events, Markovich denied, Traskovich survived crash, and the edges are the temporal relations between these events. So this event happened after this event. The prior work includes two systems, notably Kaibo and Coq-Comp-Time. They both have a multi-stage approach, so they have different components for dependency parsing and so on. Having different specialized systems means that there's a pipeline, so there's always a chance of cascading errors. Further, these systems are developed using a small corpora of documents, so 36 for Kaibo, 276 for CCT. And this lack of hand-labeled corpora is actually a major bottleneck in adapting large-scale language models for these tasks. So let's look at the task definition more formally. So G, V, E is the temporal graph corresponding to the given document D. R is a temporal relation between events EP and EQ. CR is the set of sentences in the document D that contains both the events EP or EQ. And then we tackle two tasks of different complexity. The first task that we tackle is node generation. So we are given the context CR, a source event EP, a temporal relation, and we want to generate the target event EQ. The second task is the more direct task of graph generation. So we are given a document D and we want to extract the entire temporal graph. So with the problem definition out of the way, let's look at how we approach this. There's two broad components. First is preparing data and second is fine-tuning. So let's discuss each of them piece by piece. In terms of data preparation at a very high level, we have a text corpus that we feed to Kaibo to extract dense and noisy temporal graphs. We then employ pruning and clustering techniques and encode each of the graphs to create a corpus of pruned graphs. So in terms of dataset, we use the New York Times corpus, which is a large collection of about 2 million articles spanning over 2 decades. We filter the articles to retain those that are related to violent events, just to have some notion of a domain. That gives us about 90,000 articles of various kinds. Once we have these raw documents, we use Kaibo to get some sort of a weak supervision. The good thing is it was easy to scale with Kaibo. It was pretty lightweight, which is required because we have to label about 100,000 documents. The problem is that a lot of the verbs extracted by Kaibo were noisy. So about 10% of all the events were said. A substantial amount of relations were extracted with very low confidence. And then the events are extracted as standalone verbs. So just to give a concrete example, suppose the sentence is A killed B, after which C killed A. The extraction done by Kaibo would be after killed and killed. So there is no way to really tell which of these two instances of killed does this kill, for example, refers to. So in order to tackle these challenges, we remove all the verbs that have a low IDF or are light or reporting verbs. So this is the list that we use to prune the verbs. Then we augment each verb with a corresponding noun phrase and the object following Chambers and Jurafsky's work. So as going back to the example that I showed in the previous slide, suppose the sentence is A killed B, after which C killed A. We now annotate each verb, for example, kill, with the object A and the noun phrase C. So that kind of adds more context, makes it more unambiguous. Finally, we drop all the relations that have a confidence of less than 0.5. We also remove all the vague relations. So we are left with a set of 5 relations listed here. Finally, we also notice that temporal graphs typically have small subgraphs. So for example, if the article is talking about kidnapping, there would be 3 broad stories in that article, right? There would be the beginning of the article that talks about planning, then maybe there's execution, and then finally conviction and trial, right? So those form subgraphs. So we kind of divide each temporal graph into subgraph using the notion of event communities, and then we ground each of the subdocument into these subgraphs to reduce the noise and kind of make the coupling between document and graph more cohesive. And these tuples are then added to the training data. So just to give a concrete example, this is an actual temporal graph extracted by Kaibo, and as we can see, these 4 yellow events have nothing to do with any other event in the document. So we extract this as a standalone graph and then also map it to the corresponding piece in the text. Finally, we have the documents, we have the graphs. Now we have to encode these graphs into strings because recall we want to train language models to generate these graphs. So we choose dot to represent each graph as a string. By the way of an example, here's a small graph with 3 nodes, 3 edges, and this is the corresponding dot representation. So node 1 goes to node 2, and this is the type of the relation. We have some discussion in the paper around design choices, and we found that listing these nodes in the order in which they appear in the document proved to be crucial for good performance. Finally, we have a corpus of text, we have a corpus of the corresponding pruned graphs, and that gives us a corpus of basically XY pairs. So we can train language models to estimate the conditional distribution of yi given xi using the standard mass language modeling laws. We experiment with LSTM and GPT-2 to parameterize p theta and train these language models. So now let's look at some experiments. We have 2 different data sets that we experiment with. The first is TGGen, which is just the test split of our data set. And next we have time bank dens, which is a hand labeled corpus of 36 documents from different domains derived from time bank dens. Notably, TB-dens does not have a domain overlap with TGGen, so that makes it more challenging. The baselines are, of course, GPT-2. We use GPT-2 medium for our experiments. We also used LSTM, the standard bidirectional LSTM with pre-trained embeddings, Glover embeddings. And finally, we also have Kaibo, which we use to compare the performance of our system on the TB-dens dataset. And just to quickly recall, we have 2 different tasks. We have the task of node generation, where we're given context, source node relation, we want to generate the target event, and then we have the task of graph generation. So on node generation, these are the numbers. As we would expect, GPT-2 does really well. However, we see that when we remove the context, the performance of GPT-2 drops by a lot, about 50%. On the other hand, LSTM does not seem to be using context that efficiently because its performance is about the same with or without context. So that shows that context is really important for doing this kind of node generation task. On the out domain hand labeled dataset TB-dens, we see that performance of all the systems dropped, including GPT-2. However, GPT-2 has not suffered as much as LSTM, so it shows that pre-training certainly helps in dealing with out domain settings. However, the context is now much more useful, right? Because without context, GPT-2 essentially has to use pre-training, and that leads to erroneous predictions. So the drop is much more severe without context in case of out domain corpus. For graph generation, we have several metrics. We have BLUE. We have a bunch of graph structure metrics, graph isomorphism, graph edit distance, average degrees, etc. We give details of all of these in the paper. We have the edge and node set PR and F1 score. And finally, we calculate the percentage of graphs which are valid dot files. On TGGen, as expected, GPT-2 outperforms LSTM on all the metrics. Interestingly, they both do fairly well on producing valid dot files. So in case of GPT-2, almost 94% of all the generated graphs were valid dot files. These are the numbers on TB-den. So again, TB-den is the out domain corpus on which GPT-2 was not trained. Kaivo was trained on TB10, so this is already a challenging setting to evaluate GPT-2. However, we see that GPT-2 does fairly competitively. Kaivo outperforms GPT-2 in node recall because it essentially extracts every event as a salient event. So that hurts the recall for GPT-2, but then the trade-off is in precision, as we can see here. And in the paper, we have a number of other experiments. We have human analysis of these outputs, and we also have very exciting results on predicting new events for open-ended temporal questions. So I really request you to check that out. In conclusion, it's difficult to obtain large corpora of human-annotated temporal graphs, and that kind of prohibits us from training these kind of large language models. So we develop a data generation pipeline that uses existing IE and LPN clustering techniques to automatically extract this corpus of document graph pairs. And then we propose a new formulation of graph generation task as a sequence-to-sequence mapping task, right? That helps us in using GPT-2 or any of these fancy language models to perform this task. And the experiments show that it's pretty effective. Not only does it outperform strong baselines, it also is very competitive with traditional AI techniques, and that helps us in having something like GPT-2 in-house for performing this task, which can be more readily scaled, more readily maintained, and does not have all these different pieces in the pipeline. So thanks a lot.